Hi, and welcome to day 3 of RAPID+tct 2022. I'm Brandon Ribic, the Technology Director at America Makes, and I'm really happy to be joined here today with a group of panelists, a group of experts from the AM industry. And today we're going to be talking about a subject that I think all of us want to try and understand more, is the additive manufacturing digital thread. So I'm happy to be joined by SK from AddiGuru, John Middendorf from Open Additive, and Rashid Miraj from AlphaStar. So first, thank you all for being here. It's great to see you. I know it's been a while since some of us have been together. But ultimately, I think the opportunity we have today is to kind of tap into your perspective and your expertise and experience and try and understand, some of the things that you've been working on that pertain to the digital thread, but also what really is the digital thread. I think we hear about it in bits and pieces, and because it's so vast and complex and there's so many sources of data, to me, I think it's the full spectrum, right? And it's promoting connectivity and fostering, the ability to extract data and then analyze it and better understand the underpinning physics, or maybe some other things about additive manufacturing operations per se. But that being said, why don't we all start off maybe a little bit about some things that you're doing, as a bit of an introduction, and how what you're doing relates to the digital thread.
Hi everyone, I'm SK from AddiGuru. AddiGuru provides real-time monitoring solutions for additive manufacturing processes. We focus on practical and affordable solutions, and typically taking layer-by-layer data and other data which can be easily extracted from the machines, and provide intelligent solutions and decisions to a user, so that they can go make a decision, or a decision is made for them already.
All right, I'm John Middendorf. I'm a Director of Engineering at Open Additive, and we've been working on in-situ sensing and data, handling problems for laser powder bed fusion for about the past 8 years. Really motivated by data reduction and trying to identify key data to capture during the additive process that can be stored in the digital thread permanently. Figuring out what to sense and then reducing data so you're not saving 10 terabytes for every single build, but something small and digestible for the end user.
Hi, I'm Rashid Miraj. I'm the Director of Technical Operations at AlphaStar Technology Solutions, based in Irvine, California. Come on down. 2 questions there. First thing, what is the digital thread? I see it as the computational framework for getting all these disparate manufacturing modalities to work as a kind of integrated view of what's actually overall happening. So you have the digital thread, and for us, our critical component is the digital twin, which is a part of that. So if you're talking about Industry 4.0, digital thread, digital twin come together to help that foundation. And so what we try to do is part of our role in the overall process of this team here attacking this industry-wide problem is developing deep physics tools that can address problems in a very scientific and honest, transparent way, so our customers have confidence in what we're doing, and at the same time understanding that there are computational limitations of what you can do. So we're forcing ourselves to think out of the box, because as you go down in resolution, you go down, increase your element size, explode your computational cost. You now have to think out of the box, because our customers need near real-time, then beyond real-time solutions. So it's great we've gotten to digital thread and digital twin, but the job isn't over. We got to keep pushing and make this even more effective and important to the community, so the adoption of this technology really takes off.
Yeah, and digital thread-wise, I think manufacturing, this is 21st century, and manufacturing has a big digital component to it. Now, with additive manufacturing, actually cannot exist without digital component to it, because I see additive manufacturing as a digitized process, right? You are taking apart and breaking into a small slices, and then within that small slices, one step at a time, and either lasing it or fusing it or binding it, or there are so many different processes, but without being it a digital process, you cannot do additive manufacturing. And then from the starting point of creating a CAD file, which is like, talking about kind of cradle to grave thing in a way, is starting point being a CAD file, then you obviously are, slicing its softwares, then, build, what are you doing to build a part, putting energy into it or in some form or the other, and then you're post-processing it, then you're inspecting it, qualifying it, and then obviously using it, and then you have to have all the data available to go back and look what went right and what went wrong, so further improve it, right? And then that's where I think Alpha Star comes in, is at the beginning as well, but then they can be useful at the end too. And AdiGuru is right in the middle, and then obviously Open Additive is somewhere close to us right now.
No, I think it's really interesting actually to think about the way the community has to work together, and it goes to show the importance of somebody like American Makes, where Rashid talked about computational expenses, right, and how you have to refine your models and think outside the box. And that's kind of what we do with our in-situ sensing technology, right? We had a market generated for us because people didn't understand the data they were getting. They're getting too much data, you can't handle it. So the same thing you have to do computationally, you have to do with your sensors, where you're reducing the data down to a usable standpoint. And then if we're not talking with an Alpha Star or an AdiGuru, we could be reducing the wrong things and saving the wrong things, right? And then they could be doing the wrong thing if they don't know what we can give them. So I just think that's an important point to highlight, how we do all have to work together for that problem.
Yeah, I think that's a great point. I think all of you hit on several points there. I mean, being able to speak with data, right? And then furthermore, actionable data. We all rely upon that. One curiosity I have, though, from your perspective, so we mentioned design, we mentioned processes, I think we even hit a little bit on materials and post-processing. But what about like sourcing and the actual manufacturing operations outside the machine, the workflows that happen on the shop floor itself? Are there opportunities for digital thread there, or how we connect the customer to the supplier and communicate information? For example, there's a program right now called AM Now. I think some of you are involved in or aware of. And it's very much promoting connectivity within the supply chain to effectively source. What types of digital thread information are there in those instances that we can use to help drive that actionable data?
Do you want to go ahead?
Well, you can go ahead. It's fine.
It's a big, very important question, because we're talking about improving efficiency, improving productivity, and it's not just the people building the part. As great as Open Additive is, as good as those guys are, it's still about all the people that come together that are committed to manufacturing. And the whole point of the digital thread is the connectivity. The idea that when there's data that we're sharing, how can we all use it? How can we all learn, wherever you are in the process, from how we can improve a part? And so whether you're a supply chain vendor, material sourcer, telling us the quality of the material, telling us the age of the material, when was the last use, is it a reuse? That information gets passed on to you guys to know what can you not do with it. If that information is shared with us, we can do our best to try to predict it and then give that information back to OpenApp, get it to our partners. So as long as this community really thinks about integrating that information, that integrated view, then we're really exploiting the digital thread. I'm an old school guy, and I went back to when everything was separated, and it was almost like pass the football and pass the blame. We don't have to do that anymore. Right. We're integrated now, we communicate with and we're partners not only in the production of quality parts, we're partners in moving this process forward to increase the manufacturability in the United States.
Yeah, no, we're actually working with AM now. We actually have one of their boxes, right? So we're trying to set our tools up so that we can take all of that key information about the material and the CAD model and what the sensor is detecting, and really boil it down to a level where it can go onto some kind of overarching tool, for a larger analysis than what you can get on the single machine. I think that's exactly right. It needs to go to the full factory floor, or even larger than that, possibly. So we're working with AIM now actually on figuring out what we need to send to their tool. And then SK's product is also really, really great for communicating with users what's going on in the process. So I don't know. I'll let you talk about that, but I think it's a great tool as well.
Yeah, thank you. Thanks a lot. Well, I think you hit a good point, right? We're talking about digital thread within additive, but beyond additive in a way as well. And I think that's where the world needs to go and is going, is towards open architecture so that you can plug and play with different things, and which Rashid mentioned, right? It's integrated, or now you cannot pass a football and the blame along with it. But it's not about being blamed, but we are all one, right? It might be multiple companies, but you have to work together. There might be supply chain issues with the powder for some reason or the other. There's a lot number different, this, that. Are you keeping track of it? How does it affect the builds? And things like that. And
Sure.
Yeah, and that is very important. For a part, what is the final outcome is a good, solid part which works as it's intended. And that's where different pieces come into and they plug in. Because one company doing it or one big tool doing it is also not possible. So that's why different components come in and integrate, and they can come and integrate at the front end and the back end as well.
Yeah, and I mean, thinking of inputs and outputs, those kind of relationships to me immediately make me start to think about modeling. What, I guess, a lot of people say that word though. What types of means of modeling, or what are the things that we attempt to try and model or create digital twins of for additive manufacturing? And the second question I would have is, of those, where have we seen the greatest success? Where do we see that there's high return of oh, that was great, we really want to do more of that?
Well, I mean, that's kind of what we do. It would be great to pat ourselves on the back and say, "Hoo, look what we're doing now." Mm-hmm. The final test is the customer, right? Are we giving enough to the customer that they want? When we talk about the multi-physics, when we talk about computational challenges, we have to understand that this whole science is like the mother of all sciences in one package. We have to understand in the fabrication side, and even the supply chain side, the logistical side, all of that information has to come together. But on the digital twin, can you capture the depth of the physics for whatever that modality is related to those materials? And can you get down to a small enough scale so you really have the real world reactions? Because the idea of modeling is to give you an understanding of real world application, real world feedback. To do that, I have to get the proper physics. To do that, I have to go deep down. What you find is in our available science toolset, we have the thermophysics running into the computational fluid dynamics that's hammering away at the molecular dynamics, which don't necessarily want to work together. And how do we take all that stew and make it a structural analysis problem? Whether it's part of the process build, or as the virtual part is built, subjecting that virtual part to performance loading and virtually predicting what it can do. And it doesn't have to stop at the manufacturing stage. We have to do it as a life cycle of the part. And that's where the interaction with all of us team players are in a better, by we interact, in better position to support those customers.
Yeah. Sorry.
Yeah, and I think that's simulation or modeling is close to my heart, because that's what I did in my early career. Material predictive analysis, microstructure analysis, or microstructure prediction and things like that. And 15, 16 years ago, even tried using artificial intelligence to do that, and obviously failed miserably because the technology was not there and the processing power was not there. We had to use servers and things like that, and obviously now you can do a lot more on those GPUs on a PC, a gaming PC you might have. But I think the vision I have in future, it's not executed yet, but I think we are not too far away from it. It's like what we are doing using sensors in real time and detecting issues using artificial intelligence like we are doing, and then giving a quick feedback to not only to the machine, but also that feedback can also go to the initial modeling models of the part, which could be a final element model, could be a CFD model, or could be an interaction of different aspects of a multiphysics model. It can go back and influence the design of the part, influence as well, because that can be super helpful. And I think the biggest thing in additive is that we have to bring down the cost of the making a part and improve the reliability, and all these things will help. I think we are helping each of our companies who are sitting on the table here are helping individually right now, but in the future, as we interact more and more, it'll further bring down the cost.
Yeah.
A big part of what we've been doing at Open Additive is a big part of what Open Additive is in situ sensing. And it's not just like we try to copy someone or use some generic sensor, but actually figuring out what to sense and why. And in my mind, I don't even know if everyone in my own company would agree with me or not, but in my mind, there's kind of two primary areas that you look at when you talk about in situ sensing. One is modeling to provide physics information, and that's extremely important, because if we can give accurate thermal histories in the molten state or in the solid state, what's going on in each voxel part, we can provide that information to an alpha star, and then they can use that to improve their tools. And we're not going to make those tools, so there's a big need for that kind of in situ sensing effort to develop. Then the other side is providing tools that tell you if something went wrong, where it went wrong, and if it matters, right? So that's where you get into developing sensors that are actually a lot simpler, provide smaller amounts of data, but maybe give you an indication of, this part has a problem area, and maybe help sort of quantify using tools that these guys develop to what impact that has on the build, right? So there's kind of two sections, there's like the gross defect detection and the physical modeling side. We're really trying to bring both of those together into the same set of data that's all synchronized on the process with laser position and machine health, and build that data set for the digital thread that we can pass on to people.
So, I think you bring up a really interesting thought, and I'm curious what you all think. So, I often hear the phrase modeling and monitoring. Where we are right now in the maturation of these technologies, is that what you would think would be the best approach? Should modeling be done along with monitoring? Is that a great or an ideal approach, or can one exist without the other and be effective?
Well, right now they're existing without talking to each other, right? That's the vision. In future it can help further. So we have done some surveys in the industry and asked, like, real-time monitoring, if it gives you a decision right now, how much will save you from time and money standpoint? And the answer was around 30 to 40% of their, so that's a significant saving. I can talk about monitoring from service standpoint because we did that. I'm sure you guys know your numbers, but we are providing. But I think in future that savings will increase further if it's integrated with other aspects in the business, right? And talking to each other.
Yeah, and I would emphasize what you just said, the integration. Right now, predictive tools we confident claim that we can understand what the build process is going to be, the anomalies that arise from the build process, the effect of those anomalies on the build process, and then the quality of the final part, and then come back, how do we think we can help you improve the final part? And the idea is situ monitoring, feedback control. We can take our tools and see if our predictions on a layer-by-layer basis, on a step-by-step basis, are corresponding to what the sensors are saying. So we're getting that integration. So it's an ongoing process of getting these technologies together, making them affordable to the end user, the customer, because it's ultimately return on investment. But their tools as they're evolving, they can really nicely fit together so that the modeling can support the monitoring, and together the modeling and the monitoring can ensure that the final part meets the qualification standard. And so that's how they can come together, and that's how we hopefully will be all working together in the future.
Right. Yeah. Extremely complementary. That's the word I was going to be, right? Is we can make the models better. The models can help us, better tell the end user what our sensor data is telling them during the process, right? And then there also is the pre-build aspect of it. If we can help make the model better with better data as an input, the build can be set up better in the first place, and you can start to reduce failure rates, things of that nature.
Yeah, it seems to me, I think they complement one another. There are different unique benefits to each one. I guess in terms of qualifying models or validating sensor data, is that an additional benefit to kind of packaging those two technologies as a way of kind of trying to bounce the information off the other and try and validate each one?
Yeah, answer is resounding yes.
Okay.
Why not? I think it's going to add further value to a user because our users of our softwares or our in situ monitoring or even modeling, most guys are material science guys and or mechanical engineering guys who want to go make parts. They don't want to go fiddle with the software as much. So we have to make their lives easier. That's very, very important. Otherwise, these all tools just don't get used. And if we integrate it in the right way, again, bring them together, talk to each other, and learn from each other, that's definitely is going to really accelerate the usage and also the confidence these users or additive users get out of these tools.
I would throw in one element that all that is the foundation, but our target is feedback, feed-forward control. We want to have to not just in situ monitor, but we want the whole way to make sure our parts are perfect, even if something is not where it should be. Can we correct it? Can we fix it? In that process of modeling and prediction, we're trying to get it to a point where if Open is generous enough to give us the G code and share some of the internal workings, can we then predict what a correction should be and feed that back to the instrument, work with our partners so all of that happens on a short enough time scale that it makes sense. Because nobody wants a part that takes 300 days, but we want a part compacted to reduce that time. So we are working on that side, and I think that's in the evolution of this process to ultimately get feedback, feed-forward control. But I know the parts are great come out of Open already. So.
But one thing is, if when Elon Musk takes us all to Mars, then we need to be able to print parts perfectly. So that's where it will be really, really handy.
So I think you hit on a great point there, SK. So, and based upon what you said, Rashid, thinking around feed forward, in my mind, a step before that is convincing myself using modeling and monitoring data, I can identify the range of acceptable behaviors, right, that I'm observing or quantifying as a means of quality control. Offline analysis of that data, are we at a place where we have tools that offer that type of capability? Are people looking at that to leverage modeling and monitoring as a means of assessing processes and establishing quality control schemes?
I think it's that interplay between having good in-situ sensing and the modeling people working together. I think is really the key to getting there. If a model is assuming you get into the details of the machine a little bit, right? If the model is assuming a certain spot size, certain focal properties, and certain layer thicknesses, maybe you get the model to work perfectly for one machine, but we're at Rapid. There's I don't know how many laser powder bed alone suppliers here, maybe a dozen. There's a ton of different companies and different model machines even within the same company.
Sure.
They all have different optics. Not only do they have different optics, but they may set the way that the optics focus. They may set that up differently on each model or across different suppliers. Maybe someone's in focus, maybe someone's diverging, maybe someone's converging on the plate. Maybe their gas flow is different. So if you don't have that interplay, I don't even think it's possible to set a model up to work on every machine. Like you might be able to get it right on one, but then if you go switch it to another, there's going to be hidden variables there that you don't know about. So I'm not sure exactly how they answered your question because I'm kind of getting lost in technical details there, but I think if we're going to get to that point, people with the in-situ sensing tools need to be passing that data on to the modeling guys, so they can do their job right. I mean, AlphaStar's been around a long time. They're making a great tool, but if people don't have proper data, they can't do it.
Yeah, I mean, foundation, proper data is everything. I go back to the point about forcing us to think outside of the box. And I guess there are normally about 10 to 12 parameters that tend to be the most influential in certain builds. I know, depending on who you talk to, they might be 50 parameters, they might be 150 parameters. Sure. I know Open's going to share every one of them with us. And worse than that, give somebody control of them, because you want to control the quality of the part, and then somebody that you can't touch. Like giving a 3-year-old key to the car. Good luck. But the point when I say out of the box is, if you understand sensitivities, in theory, if you understand sensitivities, hopefully each machine, say internal, same company, machine A to machine B, right, which is one challenge, or same modality, machine X to machine Y. In theory, thinking out of the box, understanding sensitivities and developing cumulative distribution and all these cute little mathematic tricks, can you go from one machine to the next? Is machine agnosticism possible? It is possible. We just have to keep working on it. Yeah. We're fooling around with tools like that. With partners, we're going to try to prove it.
Yep.
Yeah. So your original question was about a little bit about processes, right? Like how people are integrating all these tools in their day-to-day process. And that's a very good question. I don't think so. Most companies who are making parts they have a process of, okay, this is the slicing software I'm gonna use, and this is what I'm gonna do. But there are other things like our software, the RSV have some of those installs we have. It's not like fully ingrained in their process, but we have a customer here. They have a booth here, not too far from where we are right now in Rapid, and they are actually writing a standard operating procedure where they'll be incorporating AdiGuru as part of their each and every build. Certain steps they have to take. If they get a notification, then what they need to do. If they at the end of the build, they'll watch what the features that we have put out, what to do with that, and things like that. And that's great, because now it's going to become part of the process. And I think that's where slowly people are realizing that different components of digital thread are helpful to them, and that needs to be part of the process. Like the technicians and the engineers need to use that day to day, not just make a case. Oh, today I'm going to use this, tomorrow I'm not going to use this, and that just doesn't help everyone.
There's kind of a case there for like the less physics-based modeling side of things, where I can paraphrase people I've talked to that will basically say, I know what my machine makes. Like if you're building 718, right? I know what my machine makes. Just tell me if it's not doing it. And actually, I think we're, as an industry, not even there yet. But a tool like what AdiGuru does is perfect for that. It's it notifies the user that the build's not going right. And so there's actually there's different aspects of digital thread, right? And so that's, I think, more like a practical, current materials, lower, easier, lower hanging fruit, I guess.
And I think there's a lot of power in being able to take this information and use it in the decision-making process. I mean, I think there's a lot of development, be it on the product end or material development right now and where we are. But I think as we learn and as we grow, that can augment production, right? That can feed into qual and cert for sure. And one thing I want to hit upon there, just kind of turning the corner a bit, is right now, at least what I've heard in the discussions I've had in the last year or so, there's a lot of focus on physical, that is physical testing for qual and cert. But I'm starting to hear more about particularly qual by analysis. But I mean, my thing is what does that mean, and what do you think really, is that going to increase? I mean, because that's enabled by the digital thread, right? That's enabled by our understanding of actionable data.
Right. That's a vision of many people, and I think we'll slowly get there. What we can save a lot of money right now and time, as well as confidence in our part builds, is by knowing what's going wrong, if anything is going wrong, right? Right now, what Eddie Guru provides, and many other in-situ monitoring other companies also provide, you cannot replace the final quality control with that. But what we can do is we can save you a lot of time and money, like up to 30-40% depending on your processes, and that can be very helpful right now.
Sure.
But in future, as we are incorporating other streams of data, working with other companies like AM Sense suite of sensors, and bring other things together, we can get closer to that and even do that, right? On certain kind of parts, it definitely could be possible in very near future.
What I would say to that is that everything, carrying on what you said, everything starts with validation. Whether it's a coupon test to capture material properties, stress strain curves, whether it's a question about warpage, distortion, anything to do with the part, we have to prove on a building block approach that we're matching up with what is expected, what the customer wants, what the material, what it would be done traditionally in forging, casting, whatever you go. We have to get net shape, we have to get them all locked in. Once our customers have confidence, our partners have confidence in working that combined solution, then we can then go on to the next level of what you were talking about, qualification by analysis. Currently, outside of AM, we do what we call certification by analysis supplemented by test for FAA aerospace parts, composite parts, where they have to be predicted. But again, it's all based on the building block. Prove to them on the simplest element, you're being correct. Next element, until you get to the part that actually has to be done, and then predict the test, blind predict the test. Once you've done that, now the FAA believes you. In the same way, the societies we will be working with will be able to qualify our analysis to support this part. But nothing eliminates testing. Whether it's a vehicle, car, part, airplane, you've got to test it. Can we virtually test to save money? Yeah, but can't eliminate testing.
Yeah, my cop-out answer is it depends on who you ask.
That's true.
There's so many people that would be a lot more resistant to it than others. Validation through modeling. But yeah, I mean, if you go to someone building non-critical parts, they may be perfectly happy for SK and I to say, yeah, there's no defects during build, But you're saying that's obviously not enough for the FAA, and I think it's going to process. It's going to be a process. It really heavily depends on who you ask.
And testing never gets eliminated, right? You can reduce it significantly and reduce the cost there. But even in traditional manufacturing, you have to randomly test, statistical testing, and things like that. So you never eliminate that. So second Rashid's say.
Well, great. Well, I have to say I'm so happy we got this time together today. I think it's been a good conversation. We got to talk about a couple of key components to the AM digital thread. I hope our audience has enjoyed the conversation, has a bit better familiarity. I think we learned a lot about understanding the value, understanding opportunities that still exist. I think we have a lot of work to do as a community, and so I'm grateful for our time together today and all the work that we've had the chance to do together at America Makes over our 10-year history this year. And I look forward to all the collaboration to come. And thank you, gentlemen, for your time today.
Thank you.
Yeah, thank you, Brandon.
Thank you for having us.
Thanks for America Makes.
You're welcome.
Yeah, happy 10-year anniversary.
Happy birthday, 10th birthday.